Hello and welcome everyone to our monthly Quantum BC seminar series. My name is Bahia Peters. I'm the coordinator for the CREATE program that we have here, and I'm very happy to welcome our speakers for this month, two of our NSERC CREATE and quantum computing scholars, as well as PhD students in the group of Dr. Roman Krems at the University of British Columbia. We have Jonas Jäger and Elham Torabian. And I will pass the floor over to them to present their exciting research. Thank you, Elham and Jonas.
Yeah, thank you very much, Bahia, for this nice introduction, and thank you to you and Quantum BC for this great opportunity to talk about our research. So yeah, let me welcome you as well to this Quantum BC seminar talk, and it's on analytic reconstructions to power gradient-free optimization with applications in both quantum chemistry and quantum machine learning. Maybe quick check, can everyone hear me well before we get started? Here's some chat message. Okay, awesome. Perfect. Thank you for the feedback. Then let me get started. So what is the setting we are talking about here? So it's on variational quantum computing, and this is, as opposed to traditional quantum computing, this setting where we no longer have a quantum algorithm that explicitly defines how to solve the task. So for example, we no longer have an explicit quantum circuit U that would, tell us, given a problem instance, how to solve it. Instead, we want to find a quantum circuit. We want to optimize a quantum circuit that solves the task. And we describe how to solve this task by a cost function that assesses the quality of how well the given quantum circuit instance solves this task. So what we typically have is this classical quantum hybrid loop, where we run the quantum circuit on the quantum computer, obviously, and then use the output to calculate the cost function, and on the classical computer perform an update step to optimize this quantum circuit. So often we use parameterized quantum circuits. So we optimize these parameters, but we can also optimize the ansatz or the structure of the quantum circuit. So we'll cover both in this task. But this really means since we are focusing on optimization in this setting, we focus on a classical optimization routine, which is gradient free. And the applications, as already mentioned, is quantum chemistry. We're interested in finding the ground state energies of molecules using the variational quantum eigensolver VQE. And then we showcase a quantum machine learning application where the task is to embed classical data into quantum states using so-called quantum feature maps, and we want to learn these quantum feature maps, like optimize them. And then we can use quantum neural networks and quantum support vector machines for that. Okay, so when we look into other fields, like for example, deep learning, there we find that gradient-based optimizers are highly successful. And their underlying way on how to compute these gradients, or maybe quickly, the gradients are now used to inform the optimizer to just like follow the gradient into a local minimum of our cost function. And the way how you compute a gradient with a deep learning model, like a large language model or something, is using backpropagation, which is a very efficient way to evaluate the gradient. However, backpropagation does not exist for quantum circuits. So here we unfortunately have to deal with computing the components of the gradient, which is the partial derivatives, independently per parameter. So we really end up with a scaling that is linear in the number of parameters when it comes to computing the gradient, which is very different from backpropagation. But how do we in general compute gradients for a quantum circuit? So let's define this a bit more formal, in a more formal way. So we are interested in the in the partial derivative at the which is so we have the output for our quantum circuit would be the expectation value of an observer that we measure after applying our quantum circuit to an initial state psi. And yeah, so we are looking at the partial derivative, so with respect to a single parameter theta j, which is one component of the gradient, and we want to determine how the output would change at this position when varying theta j. So let's assume for now that this theta j would be an rotation angle, an angle in a rotation gate that is independent in our quantum circuit. And what we can always do when we want to obtain partial derivatives or gradients is a numerical approach, which is finite differences. Right, so we can just shift our parameter a bit and evaluate the output for this shifted parameter. Right, so then we have this. We can use this change in output to approximate the gradient or the partial derivative. And in the same way, so this was the forward difference when we step in the positive direction of the parameter. We can do the backward difference when we step in the opposite direction. Or we use something that's called central finite differences, where we have the most balanced picture here, where we step in both directions. And typically here, to be accurate, we want to choose this h appropriately small. But there's actually an interesting way to compute analytic gradients, so exact gradients for these type of quantum circuits with the so-called parameter shift rule. And this, in its simplest form, is possible as well from like these two shifts. So it really looks like central differences approximation. But for example, if we step in both directions by pi half, in the simplest form, then we have this parameter shift rule, which really is opposed to the finite differences. This is an exact expression for the partial derivative. And where does this come from? This is no magic. This just relies on the analytic form of these functions. So like the analytic form of the output as a function of the input parameter theta j, which is a simple sine curve in the case of these rotation quantum gates. And now if you look up to the number of input-output pairs that we have, like evaluations, then we have 3 evaluations, and you can also see that a simple sine curve is determined by 3 coefficients, A, B, and C. So you can wonder, okay, can we maybe use this information and the fact that we know this analytic property more efficiently? And the answer is yes, we can. We can fully reconstruct the entire output as a function of the single parameter theta j, given these 3 input-output pairs. And so here I denote this reconstruction as with this subscript theta of all of the parameters, because obviously this reconstruction depends on the other parameter values as well, but we keep them fixed, so we only vary over theta j. And then, yeah, we only need 2 additional positions for theta j to determine all 3 coefficients for this reconstruction. And this is very easy. It becomes even more clear when you look at this equivalent form here of the sine curve, which can be described as an affine combination of cosine and sine of theta and j. So you see this is just linear in alpha, beta, and A, B, and C prime. So what we actually have with 3 input-output pairs here is a linear equation system of 3 equations and 3 unknowns. Okay, and this really also goes for more complex scenarios. So for example, we might have like the same parameter occurring in 2 rotations, so no longer they're independent, or we go beyond simple rotation gates to more expressive quantum gates. Then we would have, for example, this function here, which then contains double the frequency terms, but then at the same time we no longer can use the simple parameter shift rule. We have to use a more complex one, which is the 4-term parameter shift rule. And as you already can guess from the name, we need, again, 4 more evaluations to do either, right, to determine either the partial derivative in the single point, or we can fully determine the reconstruction, because again, you can see we have now 5 coefficients in our functional form, and they can be then determined by 5 input-output pairs. And this is a general connection. So if you look at the work by Jonas et al. From 2022, this is exactly how they derive the so-called general parameter shift rule. They use the underlying functional form, which is in general some form of truncated or finite Fourier series, or it's also referred to as a trigonometric polynomial of some order. So yeah, how did we get here? We wanted to optimize quantum circuits, and gradients are often used for optimization to inform the optimizer to find an optimum by following the gradient. But this information is very local. So what essentially happens is that you locally approximate, or that you approximate your function in a point by a line. And obviously this approximation is only faithful as long as you don't go away too far from this point. But really, we can expand our view of the cost function drastically using these analytic reconstructions, because then we can see along the full domain of the single parameter theta j. So it's obviously more informative, but most importantly, we use it's the same quantum resource overhead. So we need the same number of evaluations of our quantum circuit or quantum model. That's really the key here, and this is very different from what you would find in other domains like deep learning. So yeah, so then we really want to inform our optimizer with these reconstructions. And this brings us to design optimization algorithms that are gradient free and rely on these analytic reconstructions. We have 2 scenarios for this. One is that we consider a fixed ansatz. So all of the gate positions are fixed. We only want to optimize the parameter values. And we have scenario B, where we want to also optimize the ansatz. So for example, we want to add more quantum gates to further reduce the cost function along with optimizing the parameters. Okay, so for the fixed ansatz setting, I already introduced gradient descent, where we consider all parameters simultaneously by computing the gradient, then using this gradient as an update direction to perform the step. There's a different approach, but less known for sure, which is coordinate descent. And in this, we only look at a single parameter at a time to perform an update. And there's another concept from optimization, which is line search, which is to find a good step size along the update direction that we're considering. Right. So now we can directly derive a gradient-free optimizer by combining these approaches by using coordinate descent with an efficient and exact line search. So let me show you how to do this. We would now iterate over the parameters one after another while keeping all of the others fixed in each iteration. This is exactly what would be coordinate descent, right? We only update along a single coordinate at a time. And then for this single parameter, we get our reconstruction and then determine the global cost optimum along the domain of the single parameter theta j. And this is efficient. So like the search here along the parameter using our reconstruction is the line search here. And this is efficient because we only use classical computations once we have the reconstruction, right? There's no need to query the quantum computer again because all of the information is in the reconstruction for this. And it's exact because we can perform a full step to this global optimum along the search direction. Often this information wouldn't be as accessible, so this is why line search is often not exact. And here's also a very good example where you can see the advantage of this approach conceptually in a single dimension, because the partial derivative would actually lead us to a suboptimal optimum here, minimum. And so this concept has been introduced in parts before in several works, and we will show in particular how to apply this to a certain case in quantum chemistry. Now we can also, yeah, now we will switch to the adaptive ansatz, maybe additionally optimize the ansatz. So for this, we should consider first combinatorial or discrete optimization, where you have to progress, you have to select from one of the discrete choices, and you would usually do this with a heuristic criterion. An example is the greedy search heuristic, where at each step you would go for the option that decreases the cost most. And this might be suboptimal in the long run, but it usually has very low runtime, and this is why we focus on this to be very quantum resource efficient. Okay, so yeah, using this, we can now come with a gradient-free optimizer in this setting by first defining a gate pool of possible choices, and we then repeat. And in each iteration, we would probe this gate pool by appending each gate to our current ansatz U at different qubits. If it's a fixed gate, we can directly evaluate the cost function. But if it's a variational gate, we have some parameterization. This is where our reconstruction comes in again, where we would use then a reconstruction to determine the optimal cost and parameter associated with this choice. And we would append the gate with the lowest cost, which makes it, in this iteration, which makes it a greedy search. And yeah, a special case has been introduced before in this work in 2023. I will talk about it a bit more later. And obviously, we can combine this approach with method A as well. So after appending a new gate, the previous parameters might be suboptimal now. So you might want to update them, optimize them again before appending a new gate. Okay, so now I will talk about our first application in quantum chemistry. So there, the algorithm that I basically described conceptually before is, we refer to it as excitation solve, and you will see in a second where this name comes from. And this is is a result of a collaboration with 3 other PhD students from the Quanticom team at the German Aerospace Center, DLR. And our work is available on the archive at the moment, hopefully published soon as well, and has the title Fast Gradient Optimization of Excitations in Variational Quantum Eigenservice. So let's get started with some background. What is the application here, and what is the variational quantum eigensolver? So the problem we want to solve is the molecular electronic structure problem, which is that we want to find the ground state and dissociated energy of electrons in a molecule, and we want to use the quantum computer for that. This problem is described by the Hamiltonian H. And we can obtain for any state, electronic state, we can obtain the energy the system is in, the average energy, by this expectation value. So H really serves here as just as the observable. And the goal is to find the lowest eigenvalue of this Hamiltonian, because this is connected to the ground energy. And this is where the name variational quantum eigensolver comes from. The energy we can directly use it as a cost function, right? Because our goal is to find the minimum energy, which then can be just used as the cost function. And yeah, so this variational quantum eigensolver was introduced first in 2014. And this is really like, now that you already know in general like how variational quantum algorithms work, this should be no surprise to you. We just use a parameterized quantum circuit to prepare some trial state given an initial state psi, and then we estimate the energy associated with this trial state, and based on this information we refine the state by, for example, updating the parameters or changing the ansatz. Now, quickly, how to model molecules on a quantum computer. This can be achieved through the Jordan-Wigner mapping, which tells us how to map electronic states to qubit states. And we do so by modeling the occupation of each spin orbital of a molecule by a qubit. So this means in this scenario, for example, we have two molecular orbitals that we model, one lower energy one at the bottom and a higher energy one at the top. And it is that each molecular orbital can be occupied at most by two electrons of opposite spins, which means that we model this occupation by spin orbitals. So this is why we split the molecular orbitals in two spin orbitals. So this means each spin orbital is modeled by a qubit with the Jordan-Wigner mapping. And for example, if none of these orbitals is occupied, there's no electrons present in the system, we would put all of the qubits into 0. In this case, for example, there's now 3 electrons present, we would put the corresponding qubits, flip them into the 1 state. Okay. So now how can we manipulate, like, act on these states? Because this is what we want to have a quantum circuit to act on them, to prepare the ground state. We could think of just using qubit rotations. But this has the problem that these qubit rotations are unphysical in the sense that they might prepare states that do not correspond to valid electronic states. So for example, if you think about rotating a single qubit, what this means is that we blend between between occupying and in removing the electron in a single spin orbital. And so we could, for example, obtain states that have on average only half of a qubit or some of an electron or something, which is not physical. And importantly, we usually determine in our initial state how many electrons we want to model, and we want to preserve this number of electrons throughout this preparation of the ground state. So instead, we really want to think more physically about this problem. What we're really interested in is modeling how to excite electrons from between different orbitals, and this is exactly what's modeled by fermionic excitation operators. So we want to use these. So as an example, we have then an excitation operator would always act on a certain number of electrons m and excite them between spin orbitals. What we will consider here is single excitation, so we would only excite a single electron at a time, or double excitation, so 2 of them are excited about the same parameter, theta. So it's a correlated excitation. And this already constitutes the very famous UCCSD ansatz, which stands for unitary coupled cluster, singles and doubles. And all of the higher order excitations, they could be, we can use our algorithm excitation software easily, but we usually don't need to model them for our cases. Okay, so how can we apply this optimizer here? These optimization techniques I introduced before. So let's first check the functional form. So we start by looking at the excitation operators and look at them in their exponential form. And there we can see that the generator now no longer fulfills the relation that we have for rotation gates, which was G like the generator squared being the identity. Now it's more general that we have that this generator cubed is equal to itself, and equivalently has this eigenvalue spectrum. But most importantly, we provide several proofs in the paper to see this relation, is that this tells us that whenever we perform a reconstruction in a single parameter of an excitation operator, this will be a second order Fourier series. This is what I showed in the second case earlier in the general methodology part of the presentation. This means we need 5 input-output pairs in total to get this reconstruction. Okay, so yeah, we can easily use this for a fixed ansatz. This is just then we use the VQE with the UCCSD ansatz. But we can also like switch to method B, where we want to have an adaptive ansatz. And this is related to this work from 2019, which is called adapt VQE, where instead of having a fixed UCCSD ansatz, we start with this an empty ansatz and put all of the possible operators from the UCCSD ansatz in a pool. And this works exactly as I introduced. Or like in the original work, they used a heuristic based on the magnitude of the partial derivative when appending or like probing new excitations and selecting the one in a greedy fashion that maximizes the magnitude there. But this is only assessing going for the local, like the highest local impact of adding an excitation. And we use the full reconstruction to see the best possible impact you can immediately achieve by adding an excitation. And then yeah, we optimize all of the previous parameters with the fixed ansatz method. And yeah, so this other work I mentioned before, so there it was restricted to the case of qubit excitations, which are simplifications of fermionic excitations, and but they lose certain physical properties there. And beyond that, we also provide extensions, which is to study or to optimize multiple parameters simultaneously. One has to be careful because the corresponding reconstruction is more costly to obtain. And we can support parameter repetitions in the ansatz, which is relevant if you perform multi-step tutorization in your application. Okay, so now the experimental results. So we tested excitations of across these molecules from simple molecules at H2 to H2O, and we use the STO3G basis set. Along with the Jordan-Wigner mapping, this then gives us 4 to 14 qubit systems. And we compared it to a variety of other optimizers, both gradient-free and gradient-based. What we want to achieve is the so-called chemical accuracy at 10 to the -3 Hartree, which you can see here on the y-axis there are the arrows. So this blue area is chemical accuracy. And these alternating gray vertical shadings, they signify the number of energy evaluations it takes to either with excitation solve sweep through all of the parameters and update them once, or the number of evaluations you need to obtain the gradient using the 4-term parameter rule. And now, very remarkably, is that across all of these molecules, we achieve chemical accuracy within this first sweep. So this means that we are done with the optimization before the first gradient was computed. So this is before any gradient-based method could perform a single update step. So this is very fast convergence. And on top of that, with gradient-free optimizers, they also gradient-based optimizers, they also have the step size parameter, which is very sensitive, because if you choose it too low, you have slow convergence. If you choose it too high, you might diverge. And so we also performed extensive hyperparameter study to determine a good step size for these gradient-based optimizers, which definitely adds a lot more energy evaluations there, and so this was not even shown in the previous plots because they were all with the optimal step size. And it's very important to highlight this, that excitation solve or like these grain-free optimization techniques do not have such sensitive hyperparameters. Okay, now for the adaptive case, adaptive QE, we can also see that we converge way faster than the original adapt VQE in using the gradient-based heuristic and gradient-based updates in between, adding new excitations. And we also showcased a two-dimensional variant of excitation solve here, where we append two excitations at a time, which further improves convergence here. And you can check the paper if you're interested in more in a more detailed analysis of our method. So for example, we studied molecules at different geometries by stretching the bond distance of in these molecules. And why did we do this? So this leads generally here, as you can see in the top plots, to a higher Hartree-Fock error, which is the initial error. So this means we are initially further away from the optimal solution, so the optimization gets more tricky. Or in other words, this also like usually signifies stronger correlations being present in the system. Yeah, and we also for very challenging stretched bonds in the H2O, we identified certain found certain scenarios where excitations of might get stuck in suboptimal local minima, but we could mitigate it by using variants of excitation solve like the 2D variant, or by instead of going through the parameters in order every time, we randomly shuffle them before we sweep through them again. Okay, so with this, I'm at the end of the excitation solve topic of the quantum chemistry application here. I want to highlight that this excitation solve really fills an important gap of using these very fast converging gradient-free methods in the context of physically relevant Ansätze here, as it was not the case before. Okay, and with this, I will transfer over to Elham for the quantum machine learning topic.
So hello everyone, good afternoon. So I'm going to talk about the part that we showcase the application of this analytic reconstruction for quantum machine learning. This work has been done in collaboration with Philippe Elsasser from University of Freiburg, and the paper is in preparation. So as an introduction, as I said, the application of analytical reconstruction is for quantum machine learning tasks. We focus on classification, but it's applicable to regression problems as well. And the goal in classification problem is labeling data points to predefined categories based on patterns learned from labeled data. And we apply this analytical reconstruction for quantum support vector machine and quantum neural network classifiers, and I try to learn quantum feature map for these two. And the ansatz we are exploring here is adaptive ansatz that optimize both gates outline and parameters simultaneously that introduced previously as a scenario B. So as an introduction to quantum machine learning, I start with machine learning, which aims to understand patterns and infer correlations, and can be generally categorized to supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, we learn from labeled data to predict output of the new data. And in unsupervised learning, we learn from unlabeled data to find a pattern and a structure. And in reinforcement learning, we learn from data based on the reward or penalty we get from the environment. And the goal is maximize cumulative rewards. In classical machine learning, we use classical computers to learn from classical data or quantum data. But when quantum comes to the picture, we use quantum circuits or quantum computers to learn from classical data or quantum data. And this highlighted part at the middle is the space that we are talking about in this project. We are using quantum computers to learn from classical data. And the learning task in general can be divided to discriminative learning, like classification of objects, or can be generative, like generating new sample from the data we had before. And traditionally, people are interested in quantum speed up over classical algorithms, which means that we do it faster on quantum computers. But recently, researchers are focusing on representational advantage of quantum models and believe that because of high dimensional and complex space of quantum computers and like qubits in general, might be some advantages to develop algorithms to generate data from quantum models. And the machine learning in general can be applicable in chemistry, computer vision, power system, logistics, finance, and health. So moving to quantum machine learning, I need to introduce quantum feature map. So we have a classical data, and we need to map them to exponentially large Hilbert space of n-qubit system. And in practice, what we do is that we use a unitary transformation U that embed classical data points into H as a quantum state that's represented here. And in gate-based quantum computing, it can be realized by variational or parameterized quantum circuits. So quantum support vector machine is analogous to classical SVM. Classical support vector machine tries to look at the data set of feature X and labels Y and try to find the best line or hyperplane that can separate them by finding these support vectors, which are closest points to the line, by maximizing margin. So that's the high level goal. If the data set data points is linearly separable, it's not a difficult task. But if we have a linearly non-separable data set, then you might think about mapping data points to the higher space that make them separable for you. But in classical machine learning, we have a trick named kernel trick that instead of explicitly accessing to individual data points, we look at the similarity measurement between each pair. And we assign labels to new data based on similarity to the trained data, as shown here. And quantum SVM is the part that instead of using classical computers to calculate kernel, we use quantum computers to calculate kernel. And we need a unitary U here that we measure at the end, and the measurement between two pair give us each elements of kernel matrix. And these kernel coming from quantum computers can be applied to classical SVM to predict the labels of unseen data. But the problem is that without inductive bias or any prior knowledge, it's not easy to find the proper unitary transformation that can capture the correlation between data. What we can use is we can use target alignment loss that try to maximize the similarity, try to maximize this value at the top, which measure the similarity between two classes. If two classes are the same, we expect to have the maximized value for this. And so for each quantum circuit and corresponding kernel, we can calculate this loss and evaluate it. So in quantum neural network classifiers, analogous to classical neural network that we have a layer of neurons and activation function, we look at quantum circuit as a network of neurons and activation function included in this unitary theta. And what we do is that we do the measurement at the end to find this mx theta. And then the sign directly can be found from the output of quantum circuit. Here, we don't need any post-processing. We directly use the output of quantum circuit to find the label of unseen data. And again, we need some loss function that help us to find the best unitary transformation or quantum circuit. Here, we use empirical loss, which average over all training points and could be can be calculated as a linear loss, or can be negative log likelihood. That can be, this probability can be calculated from the output of quantum circuit directly. And we try to minimize this empirical loss to find the best unitary transformation. So the algorithm we introduce here is quantum feature learning via analytic iterative reconstruction that grow the quantum feature map circuit incrementally, similar to what Jonas explained in general introduction about greedy search. But the difference is that we have a highly simultaneous optimization task, that we optimize the quantum gate choice from a pool V of n possibilities. We choose the feature from the D features of data, and we optimize weight parameter based on Tmax cost evaluation that we define. All happen simultaneously. And for example, for quantum neural network, we define this pool of gates, and for quantum SVM, we chose to use this set of gates. And traditionally, on like adaptive algorithms, all of these steps happen as a nested loop, and these nested loop all of them are evaluated on the quantum computer, and then it introduced a lot of quantum resource overhead. But in analytical reconstruction, what we offer here is that instead of evaluating parameters and selecting features on quantum computer, we use them classically using classical analytic reconstruction. So because we define this parameter of gate as the alpha, which is multiplication of feature and parameter theta, then we can simultaneously reconstruct the gate as described early in general introduction. So on the quantum computer, we build analytical reconstruction of the gate. For example, here is a rotational gate with parameter alpha. And then what we do on the classical computer, we try to find the best parameter theta and the best feature among D features that minimize this empirical risk. And then incrementally, we add that gate that can minimize the cost for us. To benchmark this algorithm, we used 4 separated data sets. One of them is linearly separable, generated synthetically. And one of them is MNEST, which is a real-world problem of handwritten digits. And we try to classify 3 and 5 in this case. And also 2 other synthetic data sets of bars and stripes and 2 curves. And you see in this table, number of training points, number of test data, and dimension of each data set we use in this study. And the color code here just show the color corresponding to the result figures that make it easier for us to follow the result corresponding to each data set. So finally, result, if we apply these algorithm to classify those 4 data sets I introduced, and we do it on the classical simulator, we see that we can get to above 90% accuracy on the test set for all of data set. There are some discrepancy and overfitting for linearly separable, but for others, the training and test accuracy match properly. And also, we use only 25 gates to do this, to apply this optimization. And if we implement these algorithms on real hardware IBM quantum computer, we need something named mini batch. Mini batching means that we use a subset of training points to train the model and to make it possible to run on the real quantum computer with limited quantum resources. So for most of our models, we see the similar trend of accuracy corresponding to number of gates. And there are but some big gap or overfitting for MNEST dataset, which is full resolution, is not like reduced dimension MNES dataset. And then this can be as a result of mini batching, because in quantum SVM, if we use a small size of the training point, subset of training point, and build a quantum kernel, we may lose some correlation and data information in the kernel, and that could be the result of that. And if I move to quantum neural network, we see that on the simulator, we see the same trend. All models for all data sets reach more than 85% accuracy on the test, and limited number of gates used. But here we have used more number of gates in comparison with quantum SVM that can be justified, because in quantum SVM we calculate kernels. We don't use the output of quantum circuit directly. That can capture the relation between data points faster. And if we implement these algorithms on IBM quantum computer, so we see the same trend and significant result for full resolution MNES dataset on the right side. And you see that there is some noise, of course, but we don't see that much overfitting or discrepancy between training and test result. Also, we see that we converge in the loss function at about 8 gates, which is very significant. So to compare, to have a better understanding of how important this simultaneous optimization is, we did an ablation study that tried to understand the influence of this simultaneous optimization of gates, features, and wave parameters. And what we did in this figure is that, for example, in the dashed line, dashed pink one, we replaced the optimization by analytic reconstruction of parameter with random parameters. And we optimize feature and gates as previous. But you see that our algorithm QFlare shows the better performance in all cases. We replace one of components of optimization in both MNES and bars and the stripes dataset. And also in all cases that we compared, our algorithm converged to the highest accuracy faster. Also, we try to see what happens if we don't apply any analytic reconstruction on the data set. And it's something that people traditionally do with greedy search. We saw that the number of quantum evaluation scales with the number of features, which is the normal way of people doing this optimization. But if we do analytical reconstruction and apply this simultaneous optimization, we see that we can converge to the highest accuracy in all cases of MNES dataset very fast and with reduced quantum resources. And this is the references that we use, and thank you for your attention. At the end, I would like to thank my supervisor, Professor Roman Krems, and our group members for supporting us, and you for hearing to listen to us. Thank you.
You, Jonas and Elham, very much. I'd like to open the floor for any questions. I know there was one in the chat earlier. Rogerio was asking about what backpropagation is. Sorry, I think my internet's being a bit weak. Asking the question in the context of neural networks or optimizers. So I'm not sure if he's still on the call, but that was a question in the chat. There he is.
I am. Hi. Can you hear me? Yes.
Yeah, we can hear you.
Yeah, excellent talk. So it was in the beginning of the talk, you were motivating new quantum algorithms for without a gradient ascent, because you said there was no backpropagation. Can you explain what you mean by backpropagation? Because you had a neural network, and if you can go back.
Yeah. Backpropagation is it's this very typical like it's a standard approach for in deep learning, where in
That's the beginning.
Yeah.
There.
where the idea is that as you compute the output of your neural network, right? This means that you forward propagate all of these inputs that you feed into this input layer, right? You step by step feed them to neurons in the through the hidden layers all the way to the output layer, and you would store certain information about these intermediate results. You don't throw them away, and then backpropagation is just, it applies the chain rule to compute the derivative, but it heavily reuses these intermediate results that you stored. And by this, it's very efficient. So you basically, let's say, because you already computed the backpropagated all of the relevant information for the gradients into your, let's say the neuron here in the first hidden layer, it is just a few more calculations to compute parameters in the first layer or something like this, instead of like going over and over again all the way from the output, right? So this is just I mean, some people call backpropagation just like a glorified application of the chain rule, because it is a very simple principle. You really just store information that are useful later, but it is highly effective. So really, like, if you add another parameter, you basically notice no difference in the runtime cost to compute this extra parameter, the partial derivative for this extra parameter.
I see. So let me see if understood. So you're saying that deep learning uses the so-called backpropagation algorithm to do gradient optimization. And you're saying that such an algorithm doesn't exist in quantum computing because we cannot make a measurement.
Yeah, exactly. This is kind of like, this is at the core, because the issue is like storing intermediate results would kind of be equivalent to measuring them. And but then you cannot reuse, like you cannot continue the computation with them. So this is really at the core, this like measurement problem. And this is why there's more or less no real backpropagation. There's a paper on it, but it addresses exactly this issue on backpropagation for quantum circuits. Yeah.
Okay,
So this is why you really like usually end up with independent computing these partial derivatives completely independently.
Okay.
Yeah.
Thank you. Yeah, that was my question.
Yeah,
Thank you.
you're welcome. Great question. Yeah, thank you.
There was one other question in the chat here. For the VQE, what kinds of circuit depths were involved?
That's a good question.
How we define depths?
So I guess by depth, I mean, you mean like how many of these operators would you need?
Yes.
So you can see this a bit. I don't recall exactly the explicit numbers. It's in the paper somewhere, but I mean, we can infer it from the number of energy evaluations we take by sweeping once over the parameters, by just checking how long these shadings are here horizontally, and dividing it by 4, because it's 4 energy evaluations that we need. So then this would, I mean, this is like, I mean, here for H2, I mean, I should know, I think it's like 3 or 4 excitations that we consider. And I mean, it goes all the way up to, here we have something like a bit, maybe like 800 parameters or something like this, evaluations. So this would be divided by for like 200 parameters, like 200 excitations. So it's quite a deep circuit, especially if you would compile it down on a hardware level. Yeah, so this is one of the disadvantages of these excitation operators, because they usually compile into deeper circuits, as, for example, hardware efficient ansatz would do. Yeah, you're welcome. Yeah, we have a question here in the room. One slide.
Oh, okay, sorry. So I was thinking backwards. It was one of the slides where H2O just never converges. I don't want to ask you about that.
You mean, so here,
It's not this one, perhaps it's another slide. This one, go back. H2O never converges. Is it the red curve is supposed to intersect?
that's a good observation. I'm not sure if it's just a matter of how we plotted it here, because I mean, this is for example, this red curve is for the gradient descent optimizer. But the gradient descent optimizer, where is it? Yeah, I think it's just not plotted. I mean, it should converge eventually.
Okay.
I'm not exactly sure because I wasn't too involved in these experiments, but I cannot tell you if we just crop the images here for visual reasons, or if we stopped it early at some point. Because I mean, you can imagine it's like actually quite like long simulation runtimes.
Do you think if it takes a while to converge? If it does, because it's like stuck in the local minimum?
I wouldn't say it's currently stuck in a local minimum because it's decreasing.
Right.
Yeah. So I guess it's just slow because of the nature of doing this like stepwise updates. Yeah.
There is another question in the chat.
Yeah. So what's the difference of an RZ and RZZ gates? That's when you consider the exponential form of a gate, then this is just an RZ gate would be you just have a single qubit Pauli Z in your exponent, and for the RZZ gate you would have the product of two Pauli operators on two different qubits in the exponent. I mean, in general, this means an RZ gate is a single qubit gate. You wouldn't introduce any entanglement, while with an RZZ gate, you introduce entanglement. It's acting on two qubits with the same parameter. Yeah, you can like break it down into like a C naught and then an RZ rotation. These things, yeah. Sometimes they're referred to as Ising ZZ operators. Okay, yeah, you're welcome.
So due to time, if there was maybe one more question, we could take it. Otherwise, we'll wrap up. Any final questions? Okay, thank you again to Elham, Torabian, and Jonas Jäger from UBC on their excellent seminar today. I'll just stop the recording. Thank you.
Thank you.